Right, today we're going to talk about angular and linear velocity primarily, and we're also going to talk about arc length. So we're looking at worksheets 1, 3, 4 out of the packet I gave out yesterday. And we're also going to refer to 11B, which is the formula sheet with the unit circle on it. Any of the formulas presented today that you would need for the final will be given to you on a formula sheet as part of the final, okay? And that formula sheet will also be provided for the quiz. All right, I am going to start by talking about worksheet 1A. Just a little bit, because I found this vaguely interesting. Probably no one else cares. But it says at the top, the input value in a trig function is an angular measure. So when we write y equals cosine of x, what we're putting in is the measure of an angle, right? If we put it in degrees, for example, 90 degrees, or better yet, 180, okay? If you put in 180 degrees, you get out a value of -1. Are those related at all, degrees and the number -1? Okay. They're related by this cosine function, but the labels are totally different. One is just an integer number, and one is degrees. That is really the explanation for why we have to do things in radians. It's hard for most of us to understand, but it says this poses an immediate problem for us when we choose to measure angles in degrees. The problem is that degrees have no mathematical relationship to linear units. So when we say 360 degrees in a circle is a radius, there is a radius of 1. What relationship does that 360 have to the 1? Okay, in what sense is it 360 times as big? Answer these questions isn't possible because a degree is another unit altogether. So radians are these incredible units that appear and disappear, I like to call them. They're magical, okay? When we measure in radians, the definition is, let me go on to this page, okay? A radian is exactly the same distance here, from here around to here, as this radius. So this value is the same as this value, then this is called exactly 1 radian. A central angle of 1 radian if it intercepts an arc with the same length as the radius. And a radian can disappear and reappear. I'm trying to find the little note about that. Here it says, so when we have this arc length formula that we're going to talk about in a second, as long as S and R are measured in the same units, the radian is unit neutral. So when we take 2 radians times a radius of 5 inches, we just get an arc length of 10 inches. The radians goes away. This is different from other kinds of labels. When you say 3 men worked 8 hours, you get 24 man hours, okay? They literally have 2 labels. Or when you divide 55 miles by 5 hours and get 11 miles per hour, you have 2 labels, okay? Here, when you do radians times inches, you just get inches. It just goes away. The same is true when we do, when we divide, you'll see we'll end up with nothing per time. For example, if we had 55 miles per hour, or I'm going to mess this up and I got to think about this. Yeah, that's not a good example. If you have an example where you end up dividing and you end up with no units per time, the unit is just radians. Okay, we'll have some of those in a minute and it'll make more sense. Sorry, I wasn't prepared to make up a very good example there. Back on the first page real quick. It talks about a central angle, which just means it's at the center of a circle. Its vertex is at the center of a circle. Does that sound familiar to everybody from geometry? A central angle is one whose vertex is at the center of a circle. And it can be measured in degrees. Degrees are 1/360th of a rotation around, and degrees are broken down into minutes and seconds. So 1 degree is equal to 60 minutes, and 1 minute is broken down like time into 60 seconds. I assigned a couple really easy questions on this concept, but we're not going to spend a lot of time on it. It's not on the final, okay? So a degree can be broken down into 60 minutes and every minute into 60 seconds. That does mean that 1 degree is actually 3,600 seconds. Does that sound familiar to anybody? An hour is 3,600 seconds? Because you'd have 60 minutes times 60 seconds. Everybody all right there? All right, so quickly, here's an example, and I am going to show you how to cheat and do this on the calculator. But and the ones you're assigned are way easier than this even. But if you have 37.425 degrees, that is 37 degrees, and then you would do 0.425 times 60. Somebody give me that answer.
25.5.
Thank you. 25.5, and that is minutes, which is really 25 minutes and 0.5 times 60, or 30 seconds. So the whole answer is 37 degrees, 25 minutes, and 30 seconds. This whole number part was the degrees. This decimal part I multiplied by 60 and made into minutes. And because it was 25.5, that 0.5 is another half a minute or 30 seconds. Yes?
So DMS is degrees, minutes,
Yes.
seconds.
This stands for degrees, minutes, and seconds. Now, there's a cheat on your calculator. No, it doesn't matter what mode you're in. The only time it matters why is this not coming on? All right, we're gonna put in, tell me the number again, 37.425?
Yes.
And then there's an angle menu on the apps button there. So we go,
0.425.
okay, thank you. We go second apps, and it says angle, and we're gonna go down to degree. We wanna change this into degrees, minutes, and seconds, so we're gonna go down to number 4. If I can get there. And hit enter, and it gives us the degrees, the minutes, and the seconds. Okay? So,
Is there a way to do it backwards?
yes. Backwards is more complicated on the calculator. Let me show you by hand real fast, and then I'll show you on the calculator. It's actually not if you've already done one that direction. Someone pointed out to me today, but let me show you. This 36 is 36/3600ths of a degree. This 24 is 24/60ths of a degree, plus there's 42 degrees. So literally type that in and see what you get. 42 plus 24/60 plus 36/3600. Is that right? I did it in my head. It's probably totally wrong. Okay. 42.41 degrees. And that's the answer. Now, let me show you how we would do it on the calculator, which I think is far more time consuming. But you would type in 42, and then you would go second angle, and there's the degree symbol, and hit enter. And then it was, anybody helping me remember? 24 second angle or second apse to get angle, down to the next, the little one tick mark or apostrophe is minutes. And then this is the tricky part. How many seconds was it? 30? 36? Okay, 36. The seconds is not in that same menu because it's really just a quote symbol. So it's over here on memory. So you have to do alpha and then the plus sign. Do you see it by the plus sign there? Sorry, I said memory, but that's the blue part. And then you type it in, you get 42.41. As someone pointed out to me last period, if you have the new operating system and you had just done one of these, it would be much faster to go back in here and just type over these, right? 42, and then go over here and make this 24, and go over here and make this 36, and enter. Okay, because finding all those stupid symbols is really a pain in the neck. It's not on a test or quiz. Now I've shown you, we can move on. All right. Next semester, we are going to do a lot of bearings questions, and if you've had trigonometry, you know just how joyful that is, but measured off of due north, we measure angles around in a clockwise direction, okay, when we do bearings questions. That's all I'm going to say about it today, because there's not one on this semester test, so we're going to move on, okay? We talked about what a radian is. Really fast, how many radians are in 90 degrees? Do we know how to do that?
Yeah, 90 pi over 2.
90 times pi over 180, and 90 goes into 180 twice, so it's pi over 2, yep. How many degrees are in pi over 3 radians? Well, pi can be replaced with 180, so we get 180 divided by 3 is 60. Part C is trying to get you conceptually, without a formula, to understand this. When you have this picture, if this radius is equal to this distance out here, then this is 1 radian, okay? If we have a central angle of half a radian, so see if Hofbauer can try to draw that half that size, okay? So this is half a radian of a circle, and the radius is 5. What do you think this is? 2.5 is right. If you cut this in half, right? That's what I attempted to do here, guys, is cut this in half. The radius is still 5, but this is now half of the distance along that arc. Does that make sense? Okay. Units, whatever this was inches, okay? Sorry, this should be inches. So this is 2.5 inches. So it says, find the radian measure of a central angle that intercepts an arc of length S in a circle of radius R. Well, they're just trying to get you to develop this formula, and I'm just going to give it to you and move on. Arc length is equal to radius times theta, and theta has to be in radians or the formula doesn't work. Okay? S is arc length, and you need to know that because I will give you the formula, but I'm not going to tell you what the letters are. You need to understand that part of it. S is arc length, so it is this distance here. This should have been labeled S if we were talking about it as an arc. R is the radius, and this is the central angle, and it must be in radians. This is already on page S equals R theta. Somebody got that one somewhere? 1B? Yes? Is at the bottom of 1B? Am I lying about that? Okay, bottom of 1B right here. A central angle theta. So let's draw a little picture over here one more time. A central angle theta. R is the radius. And S is the distance from here to here along the arc. Okay? And that's the worst arc ever. All right. Let's find this. I don't want to find the perimeter though. I just want to find the arc length. I don't know why you'd care about perimeter of a slice of pizza. I only care about area, right? How much area there is on that slice of pizza? How much cheese I can pile on there? All right. But we're going to find the arc length, S, out here. If it is a 60-degree slice of pizza, we need the formula to be in what measure? Radians. How do we change 60 to radians?
That formula right there.
Pi over 3. That's going to be our angle in here. And to find the arc length, we do the radius times the angle in radians. So the radius is 7 times radians of pi over 3. And again, 7 inches times pi over 3 radians magically is just inches. The labels just disappear. So 7.3.
We usually want like 4,000 inches, or like just leave it at 7 pi over 3.
It doesn't matter to me, okay? If it's an application question, generally it makes more sense to just type it in and get an answer. I have no idea what 7 pi over 3 looks like, but if you tell me it's 7.3 inches around the edge of my pizza, I know how far that is roughly. All right, I don't know why you measure the edge around the pizza, like I said. I just want to know how much there is there total of area, but we're going to move on. We're going to skip this question. And now we're going to talk about angular and linear velocity and do an example, and then we're going to go to the other worksheet that I passed out today because it has some really easy questions on it, and then we'll jump back over to this and do a couple tricky ones. It says okay, first of all, in applications it's sometimes necessary to convert between angular speed, which is measured in units like revolutions per minute. We are going to call this angular velocity. And we're going to say angular velocity, when we talk about that, has to be measured in radians per time. We're going to use a lot of dimensional analysis today, so please make a note of that somewhere, that angular velocity has to be in radians per time. Then there is linear velocity. Oh, this would be why I wrote it down here. No, well, this is the relationship between, but anyway. Okay, this is distance per time. Now, those are the kinds of labels. Time can be measured in minutes, seconds, hours, etc. Days, okay? Class periods. Distance can be measured in centimeters, millimeters, feet, inches, miles, okay? But the relationship between these is that linear velocity, we use this Greek letter. No, we don't. That's the wrong one. I just put it in the wrong place. Angular velocity is that Greek letter. Linear velocity is this one. It's a funny looking V. And the relationship between those is that the linear velocity is equal to the angular velocity times the radius out to that point. So this could be this if we needed it to be. But generally this will just be radians per distance. Time. Blah. I'm just going to make this really complicated by telling you wrong every 30 seconds. Okay, this is how I think of angular velocity. It's just radians per time. Linear velocity is going to be distance per time. But to find it, we are often going to have to multiply an angular velocity times a radius. One more really important conversion is that one revolution, or RPM, okay, one revolution, or revolution per minute, is not an angular velocity until we change it to radians, guys. how many revolutions, or one revolution is how many radians? Right, 2 pi. Does that make sense to everybody? All the way around the unit circle is 2 pi? Okay. So we're going to have to do a lot of this, converting 2 pi radians per minute from revolutions per minute. I'm going to go to answer this question that was on this page, only I've covered it with stuff. Okay. It said we had 36-inch wheel on his truck in diameter. That's a big tire. 36-inch diameter means what for the radius, guys?
18.
Radius is 18 inches. Good. If the wheels are rotating at 630 revolutions per minute, RPMs, we need to find miles per hour that this truck is traveling. This becomes a measurement conversion mess, okay? We need to change this to radians. You just told me one revolution is really what in radians? 2 pi. So that is 1260 pi. I'm not going to multiply that out yet. The revolutions cancel, and I'm down to radians per minute. What kind of a velocity is radians per minute? Look further up on this page. What's radians per time? Angular. So the angular velocity of his tire is 1,1260 pi radians per minute. To change this to a linear velocity, we do what? Right here. Angular times the radius. So we're going to multiply this by 36 inches. Yes, the radius. Thank you for catching that. 18 inches. Good call. All right, can somebody just do that real fast? What's 1260 times 18? We're already at a huge number, I'm sure. Don't multiply the pi in yet. We'll get to it in a second.
22,680.
22,680, like that? Pi, and we're at inches per minute. That is a linear velocity, and I wish I could tell you we were done, but that number makes no sense to you or I. Inches per minute. So the question on the worksheet says, well, we want to really make sense of that. Lucky us. So we have to change inches per minute to miles per hour. Okay, shout out. What do you know about miles or inches? Either one.
12 inches is equal.
12 inches is a foot. Where do I need to write inches so it will cancel? On the bottom. 12 inches is 1 foot. Now the inches cancel. Dimensional analysis. Okay. Now I have feet and minutes. I need miles and I need hours. 5,280 feet goes where? Is equal to 1 mile. So now feet cancel. Okay, I don't want minutes either. I want what? Hours. So what do I need to put? How many minutes will cancel with hours? 60 minutes is 1 hour. All right, guys, to type this in, we have 22,680 pi times 60 in the numerator, divided by a 12 and a 5280. So you need those in parentheses, or else you need to type them divided by 12 and then divided by 5280, or you can type the whole top and the whole bottom and then divide, whatever works for you.
Tons of pi in there. Right?
Yeah, go ahead and put the pi in, because it will make sense to us. 22,680 times pi times 60 divided by a 12 and a 5280. $67.5, anybody?
Yeah.
Okay, 67.5 miles per hour. just to preview that we did this correctly, I'm gonna flip to the next page real quick. 67.5 miles per hour, okay? And yes, they did just as much crazy converting as we did. All right. On to, go ahead.
So will we get those converting factors?
Generally, no. I don't think you have to know them.
You might have to know
The-
the 5,000.
Yeah, 5280 would be the only one I would even think about giving you. You better know 12 inches in a foot and 60 minutes in an hour, okay? 5280, if you needed it, I might give it to you. I don't think I ever have in the past, so either you don't need it or I expected everybody to know it. All right, degrees, minutes, and seconds, you should be able to do now. Honestly, you could just do 23 and 12/60ths because there isn't even seconds on this question. All right. Also on 3B, converting 21.2 to degrees, minutes, and seconds is 21 degrees, and if you did 0.2 times 60, you would get the minutes. Okay, which I think is 12 minutes, that seem right? Or you can do it by typing it in and using the degrees, minutes, and seconds conversion. All right, I'm skipping all the way down to this section. Will you make sure by 25 to 32 it says this on your paper? This is the formula for all of these. S equals R times theta. But they must be in radians, which is in really good shape till you get down here. Just look at 29 real fast. If S equals R times theta, what are you going to do on number 29? Divide. When you take 3 meters divided by 1 meters, you just get 3 as your theta. If there is no label, what does that measure in? Radians. So the answer to 29 is 3 radians. If it was a decimal, it would still be radians. Radians do not have to have a pi. Okay, they don't need to have a pi. Sometimes they do, sometimes they don't. Number 31 and 32, there's a problem. What do we have to do before we can solve those? Yeah, we have to make this into radians, so this will be 20 pi over 180 radians. And then if this is S equals some R times theta, what do we have to do? Yes, it's going to be S over theta equals R. So 40 divided by 20 pi over 180, which I should have reduced, but I didn't. Yeah, it's pi over 9. So you're actually doing 40 divided by pi over 9. If we want to do this in our head, it would be 40 times 9 over pi, which is 360 over pi. But I'm fine with a calculator. What is this come out? Anybody know? Should be around 120-ish. 114? Point? 0.6, okay. And that was, what did we find again? We found the radius, and the original arc length was in centimeters, so this answer is in centimeters. Sorry, I don't have much room there. So this was 114.6 centimeters. All right, I'm going to do one evil question, and then we're going to go do some easy ones on the worksheet. We're going to do, on the next page, I think, this automobile design question, number 44. Is this on 4A, guys? Okay. On 4A, it says, this table shows specifications for the tires that come as standard equipment on 3 2013 all-electric vehicles, the Nissan Leaf, the Chevy Volt, and the Tesla S. Okay? These are the diameters of those tires on those cars. The speed of each vehicle in miles, we're to find the speed in miles per hour when the wheels are turning 800 revolutions per minute. The speed will depend on the radius of the tire. Okay? And then we're gonna talk about what happens when you illegally change out the size of the tires. We're gonna start, I put it on another slide here so we had a little more room to work. The first thing I need is a radius for each of these. How do you get from a diameter to a radius?
5 by 2.
Okay, can somebody help me out?
1.75.
You're not allowed to switch the size of your tire.
Say that again?
You're not allowed to switch the size of your tire.
No. We'll talk about why in a second. It won't tell you the right speed and it won't tell you the right number of miles you've traveled on your odometer.
Is that tire spread out?
13.85.
Thank you. We're gonna talk about what, I'm gonna show you what happens, okay? So, all of these cars are turning 800 revolutions per minute, okay? The wheels are turning 800 revolutions per minute. So, I'm gonna write down here the Leaf, the Volt, and the Tesla. And I'm gonna start out with 800 revolutions per minute for this one. And what's the first thing we have to multiply by? Okay, 2 pi radians per revolution.
60 over 1. Yeah. I mean, 1 over 60.
To get,
I mean,
60 over.
yeah, 60 over 1. Sorry, to get the hours first.
yeah, doesn't matter what order. I'm just concerned that you're gonna forget you have to have radians to do this
Oh.
question, so that's why I'm starting out with that one. But yes, from here on out, I don't care what order we do it in. Actually, I do care a little bit, because to get to a linear velocity at all, you have to multiply by the radius along the way somewhere, okay? So can we put that in next? I'm gonna put the radius in here, 12.75 inches. So now my radians magically disappear, and I'm down to inches per minute. Now, Amber wants us to get rid of minutes, so I'm gonna say 60 minutes is an hour. And then I'm like out of room. Did I just totally, don't write that down. She said multiply by 60, and then I wrote it down wrong. Till I went to cancel it, then I realized it wasn't gonna cancel, right? Minutes, top and bottom. Somehow I have to squeeze in here 2 more conversions, guys. What are they? I have inches.
12 inches.
Okay, but first I have inches, so I gotta go 12 inches is 1 foot, and then inches cancels. And then 5,280 feet is 1 mile. Feet cancels, okay. Start typing. 800 times 2 pi times 12.75 times 60, and then divided by these two things in parentheses. Go ahead and type the pi in as well. 800 times 2 pi times 12.75 times 60 divided by parentheses 12 times 5280. I got 60.7. Anybody else get that?
Yeah.
Okay. So this is traveling 60.7 miles per hour, and I'm going to write it over here because that's where I have room. That's the Leaf. Is anything going to be different for the Volt? Only the radius. Yep. Can I cheat and not rewrite all that? Okay. We just need to replace that number with a 13.15. So 800, I know you guys are just copy and pasting. I have an old calculator here. 800 times 2 pi times 13.15 times 60 divided by 12 times 5280, all in a parenthesis. 62.6, anybody?
Yeah.
And the Tesla gets a radius of 13.85. $65.9, anybody? Okay. I want to talk about this. Does everybody know what the odometer on your car is? It's what measures, like, you're at 20,000 miles, so you need a new set of tires or whatever, or 5,000 miles, you need an oil change, whatever. Okay. The odometer and the speedometer, which we are all well aware of how that works, or what that does, because we watch it like a hawk, because the cops are behind us all the time, right? All right. Those two things are based on how many times the tire turns. Revolutions per minute is how those are measured. So when you change the tire out on your car, if you decide to put the Tesla's tire on the Leaf is basing that off 800 revolutions per minute, so the speedometer will say 60.7, but how fast are you really driving? 65.9. Okay? It also means if you drive for 1 hour, the car thinks you went 60 miles and you really went 66. Which means if you did that 1,000 times, you'd have 60,000 miles on the odometer when you really drove 66,000 miles. Okay? That's why it says unwise and in some cases illegal to equip a car with vehicles of a larger diameter than those for which it was designed. Okay? I'm not going to make us write a big essay here. Let's just go with the fact for part C. You can skip part B altogether, but for part C, I'm just going to write here, if a Nissan Leaf were equipped with Tesla's tires, how would this affect the odometer and speedometer? I'm just actually going to go with the speedometer. When traveling, or when let's say when the speedometer said, sorry, I didn't phrase that well. What was it, guys? 60 point something, I forgot. 60.7? 60.5? 60.7? You would really be driving it was almost 66, 65 point. Okay, is that good enough explanation? We kind of get the idea? Yes.
Well, the same goes with like you put two small tires and you have to look at
Yes, if you replaced the tires with smaller tires, then your speedometer would be off in the other direction, yes.
Because my friend, she gets them 5 miles over the speed limit, they go to speed limits.
So how do people like man traffic and put crazy big tires on there? How do they get away with it?
I don't know if it is illegal, obviously not in the state of Illinois to put bigger tires on, but they're going to have to be really careful what they're driving.
Actually, you can.
Do you know Jack Olden's?
You can adjust it.
My neighbor got a really old
Yeah, but
one
when
and
you
his
don't have
speedometer didn't work at all. Either did his like gas.
Gauge, yeah. All right, guys, I'm going to flip over to this worksheet, and I just want to have you write some formulas. This worksheet is very, very, very basic, okay? It's just plugging numbers into formulas, so I'm going to tell you what formulas to use, and then you should be able to do this one. Does that make sense?
I don't know.
The first ones, it says formulas work with angular measures in radians only. Find a central angle is given and a radius is given. Find the arc length S. Anybody remember the formula? Okay. But what if they give us degrees here for number 2? We got to multiply it by a pi over 180 before we chuck it into the formula here and get an arc length out, okay? Everybody thinks they can do 1, 2, and 3 now?
Maybe.
All you're doing is multiplying r and theta after you've changed them to degrees. Okay. Is this radians or degrees number 5 when it says theta equals 2.5?
Radians, because it doesn't different.
Yeah, it doesn't have a label, so it is already in radians. And it wants the angle in radians, but how do we find what? No, it doesn't. Find the radius. It would be so much better if I read the question. How do you find the radius given the arc length and theta?
S divided by radians.
Yeah, you're still using this formula, but would be s divided by theta will give you the radius, okay? All right, 7 through 9, I mean. Our area of a sector, which we have not yet addressed and not on our final, but this is the really important one about the pizza, remember? Okay, this is the area. And the area formula, did anybody see it on 11B? Do you see one that says area on 11B?
It doesn't look like any.
What does it say?
Half r squared theta.
Okay, so this is what you need to use to find the area of the sector. It's how much area is in here. But again, this only works when you have radians. So you need to make this one 90 pi over 180, which is also pi over 2. So for this one, we do 1/2 times 4 squared times pi over 2. Somebody type that in real fast. I just want to do one of these for you. Is it 12 point something? I think it's 12 point something, isn't it? 12.6, and it's square inches. Area is always square units, and the only units we had in the problem were inches. All right, that's how you do 7, 8, and 9.
10 is 2 pi thirds, right?
Say that again?
9 is 2 pi thirds, right?
Yes.
Okay.
All right, and 10 and 11 are also arc length and area questions. I want to go on to 12 and 13. I'm just going to use dimensional analysis because I'm too lazy to think about a formula. If I have 30 feet per second and I want to find a distance covered in 3 seconds, what am I going to do with those numbers? Because what will happen?
Seconds will cancel out.
And I get 90 feet is the distance covered. So 66 feet per second times a minute. Well, what am I going to put in place of a minute? 60 seconds. I don't know what that comes out, but it's so many feet. How much?
39.
Oh, you already did it, or?
Yeah.
I thought you would just do that off the top of your head. I was like, you need to be on math team. All right, do we still have 2 minutes? I'm actually going to tell you you can cross out 14 and 15. Yay me. And 16, 17, and 18, how do you change revolutions per minute to an angular velocity?
Times it by 2 pi.
Yep, you just multiply by 2 pi radians per revolution so that you end up with 12 pi radians per minute, and I don't care if you just leave it that for that question.
We do it for all of them, just multiply.
Yep, just multiply by 2 pi. All right, tomorrow we will do a couple more examples off both the worksheets and off this worksheet, and then we're going to talk about the identities. Yes.
Yeah.